Okay, folks, these are the solutions to the worksheet. So write a position function for Aria. People find that a little confusing because it doesn't seem like you're solving for something, but that just means you should have an equation with an input, which is time, and an output, which is x. And since there's two objects, we need a subscript on the x to say this is the position function for Aria. Okay, so this is the general formula for position function, which you get. And then this is the order in which you want to make decisions about what's happening. So x naught is where she begins, and she begins at 0. V naught is her speed and direction, and her speed is 10, and it's going to the right, so that's a plus 10. T is the input, so we're just going to leave it as t, so we can plug in any t we want. A is what the environment is doing to her, in this case, the brakes. She's slowing down, which means the acceleration has to have the opposite sign as the velocity. So that is negative 1.5 t squared over 2. Don't forget the 2. Okay, and then you can rewrite this as 10t minus 0.75 t squared. Just take that and reduce it to a single decimal. So people don't like this because they're like, I haven't solved a problem, but this is the answer. We wrote a position function where you're going to input whatever time you want in two different spots, and you're going to get a location of where she is. Okay, so now let's do the same thing for Miles. Miles is a little bit trickier because he's going backwards. So his initial position is at 100, right? Once you've decided this is 0, imagine unrolling your measuring tape. You can't restart the measuring tape here. So he is 100 meters to the right of what we've locked in as 0. He is going backwards at 5, so minus 5t. So he's heading west at 5, and he's speeding up. Since he's speeding up, his acceleration should have the same sign as his velocity, which in this case is negative. So minus 3 t squared over 2, because in order to speed up, he needs to be pushed that way, and forces cause the acceleration. So he's being pushed that way, which is negative. Okay, so then to reduce that, that's 100 minus 5t minus 1.5 t squared. So that is his position function with the xb included. Okay, so we have two position functions, one for each person. That's the hard part. Question C is calculate where she is at t equals 5. So that is what physicists call plug and chug. We're just going to plug in the number 5 to the function. All right, and then crank that out on your calculator. She is at the location 31.25. All right, and then we're going to see where he is. And then we're going to check our work just for efficiency. So we're just going to plug in 5 to his position function. And he's at 37.5 meters. So they're close to having met, right? They're both in the 30s, but she's still behind where he is. So let's go check the graph. At 5, this is where she is, and this is where he is. So he's just that little bit ahead of her. And she hasn't turned around yet, and he doesn't turn around because his vertex is in negative time. She's turning around because she's slowing down. He's only going to speed up backwards. All right, what else we got going on? Okay, now we're going to write the velocity function for Aria. And in 2025, you were supposed to listen to the play pause it to learn about velocity function. We already know that it's linear because of the video lab that we did. We got a line. So this is our velocity function that is a line because there's no t squared. So her initial velocity was 10 minus 1.5 t. All right, so that's a function. You will input a time and get out a speed. Input a different time, get out a different speed. Okay, velocity function for Miles. His initial speed was, here it is, -5. And he's speeding up backwards, so these two have to have the same sign, t. Okay, so plug in a t, get out a speed. Notice the t doesn't have subscripts because time passes the same for both. All right, now we're going to see how fast she is going at 5. So we're going to evaluate the function of 5. So 10 minus 1.5 times 5 is 2.5 meters per second. And that makes sense because she's slowing down and she was going 10. Now she's going 2.5. So if we go back and look at what's happening at 5, the slope of the line right here is 2.5 because we're really close to the vertex. We're not at the vertex yet, so it's still positive, but we're in the shallow part, whereas the slope right here was 10. So hopefully that's making sense to you, how this is steeper than that. All right, let's figure out how fast Miles is going at 10. I'm sorry, at 5. So his plugging into his velocity function, you can't see it on the screen anymore, but -5 minus 3 times 5 is minus 20 meters per second. So again, hopefully I want this stuff to make sense to you. 3 is twice 1.5. So he's speeding up twice as quickly as she is slowing down. So that's why his speed is already at -20. He started at -5. His speed is -20 after the same amount of time has elapsed. And if we go look at, you can see that this green slope is way steeper than the blue slope because he is farther away from the vertex. His slope is much steeper because he's speeding up faster. You can see he's speeding up faster because he has a more extreme parabola and hers is more shallow. Okay, so all that call back to for unit 1. Okay, now we're going to find her average velocity. We're going to do this lazy, clever, and attractive way. We're going to have the numerical average of the beginning speed and the final speed. At t equals 0, I have 10 for her. Yeah. She was going 10 meters per second at t equals 0. And then she had slowed down to that shallow 2.5, but it was still positive, right? And we're going to add those two up to 12.5 and divide by 2 and get 6.25 meters per second. So going back to her graph, another way, it's getting a little bit busy and up here, but another way to have calculated her average velocity is to find the slope of that line. Unfortunately, that's in black, so it's hard to see. But that slope right there should be 6.25. If we did, if we did the coordinates, which makes sense, right? I hope that orange line is steeper than the blue line. We know the slope of the blue line is 2.5. The slope of this orange line is 6.25. And the slope of this other orange line that we'll make green, that slope is 10, right? So most steep, less steep, even less steep. But this orange is the average because it's connecting 2 points. On average, she went, well, it's averaging a whole bunch of instantaneous speeds, or on average, it's her distance, which is her rise over the time, which is the run. Okay, so hopefully lots of things that are connecting to each other. Okay, and then we're going to check our work using the don't know, don't care about acceleration equation. Lots of ways to check your work. So x of Aria is if she has a head start plus average velocity time. She started at the origin, so she does not have a head start. Her average velocity is 6.25 meters per second. And we are all of this thinking about what happens at t equals 5 seconds. And you get that she is at 31.25 meters. Check. That's what we got before. Okay, we'll do the same thing for miles, just to keep practicing. So this is so you can go on autopilot. So his average velocity is the algebraic average of two velocities. He started going backwards at 5, and we're adding his second velocity, which is also backwards. Right, so we're numerically adding two negative numbers. So we get negative 25 over 2, or on average, he was going backwards at 12.5, right? He started out going slower than that, ended up going faster than that, which averages out to 12.5. So he gained as much ground as if he was just doing this at a constant rate instead of starting here at, starting slow and ending fast. Okay, let's check his position function. He did have a head start of 100 meters. He is going backwards on average in that time interval at 12.5 meters per second. Since this is only true for that time interval, you've got to plug in the time. You can plug in any time here, right? The regular position function, you can plug in any time you want because that's not defining a time interval. This equation, you have got to plug in the time that matches the time interval that over which you took the average. Okay, and he didn't go backwards 37.5 meters. He is at the location 37.5 meters. There is not a negative sign there. I have no idea why there's a negative sign in my key. Sorry about that. All right. Moving on. Use the velocity function to determine the time she comes to rest. Again, she was pretty close to the vertex at 5, and you can eyeball this. Looks like it's somewhere between 6 and 7. So her velocity function, this coming to rest means the output of the function is 0. That's where she is. She's not moving. Okay, so be careful. There's two different V's, right? There's the output and the initial. She started going 10, and she was slowing down, so we know she is going to reach the vertex, and we're looking for that time. So we're going to subtract 10 from both sides. So t equals minus 10 over minus 1.5, or 6.67 seconds. In 2025, that was not intentional. This worksheet is old. So that 6, that 7, 6.5 would be here. So it, the vertex is about there. So it all checks out. Yay. Okay, so lots of ways to check your work. Okay, and then we're going to find the velocity function of the time he comes to rest. So watch what happens. Here's his velocity function. Sorry, here's the general velocity function. Coming to rest means the output of your function is 0. He was going backwards at 5, and he was gaining speed at a rate of 6 meters per second squared, and then we divide by 2. Let's watch our math. We're going to add 5 to both sides. And so t equals 5 over minus 3 equals minus 1.67 seconds. So if you got this on a test, if you got a negative time, well, let's talk about what it means here. I put the whole parabola on the graph for you so that you could see -1, -2, -1, a little bit beyond. That's the vertex, right? -1.67. So I put it on this worksheet so you could check your work and see that that's what the negative time means. It means the vertex was over here. It was before we started caring about miles. Sorry, Miles. If this happens to you on a test and you know that it should have happened in positive time, go check your work. Don't go, okay, I made a mistake. Time can't be negative. This must be positive. This must be positive. And change this 3, because now you're telling me that these two have opposite signs. So he's slowing down. And so you'll lose points because that's bad physics, right? So if you made a mistake and time, like maybe you made a math error and time should have been positive, you got negative, don't go back and just arbitrarily make things, change the signs of things until it comes out the way you want. Okay, what I want you to do is say, I know time can't be negative. You know, I might have made a mistake. Go back and try to find your mistake, but don't change something that you know is right. You knew he was speeding up backwards, so these have to have the same sign. Okay, hopefully that makes sense to you. Okay, look at that. We're almost done. Then we're going to plug your answer to K into her position function to find the height of that vertex. So evaluating Aria's position function at 6.67 seconds is 10 times 6.67 minus. Okay, and then clearly this, I'm just looking off my key here, but you would have, like, this isn't coming from nowhere. This is coming from the position function. And you get 33.3 meters. Let's go check our work with the graph. Here's 30. Okay, here's the vertex was about here. And then again, if you had a ruler, you could read over. So I'm just going to take a straight. So if we just read this over, see how that is at about 33 meters. Okay. So you can check your work. Boom. All right. So lots of ways to hopefully tie this back into stuff we've already done. They both had negative acceleration, so they're both concave down parabolas on our position versus time graph. Miles had a bigger acceleration, so his parabola is more narrow. What's true here at the peak is that v equals 0, positive speed here, negative speed there. All right, but hopefully these equations are feeling like the hard, easier to deal with than graphs. But you got to be really comfortable with the different velocities, the initial speed and the output, and positive and negative signs. That's where most people lose the most points, is positive and negative times. All right, hopefully this is making sense, and thank you for listening.